Hey folks, my name's Nathan Johnston and welcome to lecture 14 of Advanced Linear Algebra. So today we're going to be learning about isomorphisms, and this is one of the rare topics in this course that did not have a direct analogy from the previous linear algebra course that you took. Okay, so for example, we learned about vector spaces right at the start of this course, and it was just a generalization of Rn. Last lecture we learned about invertibility of linear transformations. It's just a direct generalization of invertibility of a matrix. Well, isomorphisms, it's really a brand new idea to help us get a better grasp on the fact that there's so many different vector spaces out there. Okay, and the idea is, even though there are lots of different vector spaces out there, a lot of them look the same in some sense, or doing linear algebraic calculations on them is the same. And we've already seen this idea a little bit. Remember that what we've been doing recently is we constructed coordinate vectors of vectors, right? You start off with some vector in a vector space and you constructed a coordinate vector out of it by using some basis. And then we had this idea that you could solve a linear algebra problem in V itself by instead doing something involving the coordinate vectors. So in a sense, the coordinate vectors, they were the same as the original vectors. They just were maybe easier to work with because we like working with lists of numbers. Okay, well, the idea behind an isomorphism is very much the same. An isomorphism is just a function that takes you from one vector space to another equivalent vector space that's maybe easier to work with. All right, so here's the definition for today's lecture, okay? What an isomorphism is and what it means for two vector spaces to be isomorphic, okay? So here's the setup. You've got two vector spaces, don't have to be finite dimensional, can be any old vector spaces, as long as they're over the same field. You have to be working the same scalars in both of these vector spaces. Well, then we say that these two vector spaces, they're isomorphic if there's some invertible linear transformation going between these vector spaces, okay? It doesn't matter what the invertible linear transformation is, it's just there has to be at least one invertible linear transformation from one of the vector spaces to the other, okay? And if this happens, we say those vector spaces are isomorphic, and we denote it like this, V sort of equals W, because we think of it like V and W, they're kind of the same. Like, they're not exactly the same, they're not necessarily the same vector space, but they're very, very similar to each other. Okay, and the invertible linear transformation that we found that showed that these vector spaces are isomorphic, we call that an isomorphism between those vector spaces. Okay, so this idea is best illustrated by an example, why this corresponds to, the vector spaces being the same in a sense. All right, so sort of a standard example is consider the vector spaces M1n, in other words, the matrices with one row and n columns, and Mn1, so the matrices with n rows and one column. So in other words, the row vectors and column vectors respectively. Okay, let's show that these vector spaces are isomorphic. Okay, so how do you show that two vector spaces are isomorphic to each other? You just find some invertible linear transformation between them. And in this case, there's a very obvious linear transformation that's invertible between them. It's one that we work with all the time. It's the transpose map, right? If you take the transpose of a row vector, you get a column vector, and that's invertible because what's the inverse? Well, it's also the transpose map. If you take the transpose of the column vector, you get back to the row vector. Okay, and we already talked about in previous lectures how the transpose map is a linear transformation. So yeah, this is what we need. This transpose map is an isomorphism between these two vector spaces, so they're isomorphic to each other. So we can write M1n is isomorphic to Mn1. Okay, and certainly, like, these two vector spaces, they feel the same as each other as far as linear algebraic properties are concerned, as far as vector addition and scalar multiplication are concerned, right? All they are is vectors, but oriented in a different way. Like, the column vectors are oriented up and down, and row vectors are oriented side to side. But I mean, as far as scalar multiplication and vector addition are concerned, it doesn't matter the way that you arrange the numbers, right? So the way you do linear algebra in these vector spaces is the same. So they're isomorphic. All right, let's do another example, or rather, let's talk about a sort of a ramped up version of this example. Both of these vector spaces, so the row vectors and the column vectors, they're actually both also isomorphic to just Fn, okay? So remember, Fn, that's just a set of vectors as in lists of n numbers. All right, so we usually use slightly different notation for these three vector spaces, right? M1n, the row vectors, we usually denote them like this with square brackets around them. Mn1, again, column vectors, also square brackets around them, because really they're matrices, okay? And whenever we care about shape, we use square brackets. Whereas Fn, the list, vectors, lists of numbers, we don't care about the shape of these, okay? And whenever we don't care about shape, we use round brackets, okay? These really are vectors, they're not matrices. Right, but all of these vector spaces, they're isomorphic, and they're isomorphic in sort of an obvious way. You can define linear transformations between these just by, well, writing the vectors in a different orientation, or maybe using different brackets, right? An isomorphism from m1n to fn, for example, is just the function that changes the type of brackets that you have on the left and the right. Okay, and of course that is a linear transformation, and it is invertible. To invert it, you just change the type of brackets that you use back. That's an invertible linear transformation, so it's an isomorphism. So these spaces, they're all isomorphic to each other. They're all essentially the same, even though technically they're not quite the same, but they're the same enough that we call them isomorphic. Okay, so in a sense, this is sort of the idea here. Vector spaces, they're isomorphic if they contain the same vectors, just maybe written in a different way. That's the idea here. Like, there's some slightly more exotic examples than these ones, but that's the idea. They have the same vectors, but just different labels on the vectors. And the isomorphism, that invertible linear transformation between them, it just changes the labels from the labels that you use in one space to the labels that you use in the other space. All right, so let's maybe look at a slightly more complicated example. All right, let's show that P3, so the space of degree less than or equal to 3 polynomials, let's show that that's isomorphic to R4, you know, list of 4 real numbers. Okay, and again, to show that two vector spaces are isomorphic, you just have to find some invertible linear transformation between them. All right, so I'm just going to come up with one, and it's just sort of staring at us in the face when you write down what the vectors in these two spaces look like. The members of P3, what do those look like? Well, they look like a plus bx plus cx squared plus dx cubed. Well, how can I map that to R4 in a reasonably natural way that is invertible? Well, just list out those 4 coefficients here, right? The A, B, C, and D, and throw them into a vector with 4 entries. In other words, throw it into a vector that lives in R4. Well, it's straightforward to show that that's a linear transformation, and furthermore, it's invertible because you can map back the other way. The inverse function, the inverse linear transformation, just sends a, b, c, d to that polynomial that we started with, a plus bx plus cx squared plus dx cubed. And again, that's a linear transformation. All right, so yeah, there's an invertible linear transformation between these two spaces, so they're isomorphic to each other. That's it. That's all you have to check. We found some invertible linear transformation between them, so we're done. Okay, and one really nice thing is, back when we introduced coordinate vectors, really what we did was we showed that every finite dimensional vector space, it just looks like Fn, right? This is really what we're doing in this example here. We're taking a polynomial, degree less than or equal to 3, and we're just representing it in the standard basis. That's all we're doing, right? You're taking coefficients of a linear combination in the standard basis. All right, the same thing works in more generality. So that's what our next theorem is. Suppose that you've got some n-dimensional vector space over some field F, okay? Well, then that vector space is isomorphic to Fn, okay? And this, we've been implicitly doing this for a little while, but finally we built up the terminology and the technology that we need to actually pin this down as a theorem. Every n-dimensional vector space, every finite dimensional vector space is isomorphic to the vector space that just consists of a list of numbers. All right, so this is really, really nice, but how do we prove this? All right, well, again, to show that two vector spaces are isomorphic to each other, what you've got to do is you got to find some isomorphism between them. You got to find some invertible linear transformation from one to the other. All right, so the way that we do that is just sort of what we've hinted at here. Let's use coordinate vectors. Okay, let's consider the linear transformation that sends v into Fn, and it's going to be defined by, well, it just sends v to its coordinate vector with respect to whatever basis you like. It doesn't matter what basis you pick. It's just, there is a basis, great. Use that one. Okay, so that's our linear transformation. Now, to show that these two vector spaces actually are isomorphic to each other, we have to show that this function here, this t, is a linear transformation, and we got to show that it's invertible. If we get those two things, then great. These two vector spaces are isomorphic to each other. All right, so how do we do that? Let's start off with the fact that it's a linear transformation. All right, so we want to show that t of v plus w is equal to t of v plus t of w. And similarly for scalar multiplication, we want to show that t of cv equals c times t of v. All right, well, just plug in what t does. And so what we want to show is that the coordinate vector of v plus w equals the coordinate vector of v plus the coordinate vector of w. We talked about that a couple weeks ago. That's a property of coordinate vectors that we talked about just as soon as we introduced coordinate vectors. So that's true. We're happy with that property. And similarly for scalar multiplication, right? T of CV equals C times T of V. Well, that just means the coordinate vector of CV equals C times the coordinate vector of V. And again, we talked about that property back when we first introduced coordinate vectors. That's true as well. So yes, this function here that sends a vector to its coordinate vector, that's a linear transformation. All right, the second thing that we got to show that this t, this function that sends a vector to its coordinate vector is invertible, okay? And the way that I'm going to show this is, well, let's go back to the end of last lecture. Let's go back just to the very, very end when we talked about invertibility of linear transformations. And we mentioned this property here, that if you have a linear transformation between two finite dimensional vector spaces with the same dimension, well, then that linear transformation is invertible if and only if T of V equals 0 implies V equals 0. Okay, so that's a property that we're going to use here. Okay, that's how we're going to show invertibility. So let's come back down here now. All right. So first off, do these vector spaces have the same dimension, V and Fn? Well, yeah, because we said V is an n-dimensional vector space, and Fn, well, yeah, that's n-dimensional, right? Okay, it's just got the standard basis, which has n members, so that's n-dimensional. All right, so they have the same dimension. We're happy with that part. Now we've just got to show that T of V equals 0 implies V equals 0. All right, well, what is T of V? That's V with respect to B. That's the coordinate vector, okay? So if this coordinate vector equals 0, I'm going to show that that implies V equals 0. How do I do that? Well, you just do it straight from the definition. V of B equals 0. Well, that just means every coefficient in the linear combination where you represent V as a linear combination of the members of B, every coefficient equals 0. Okay, so in other words, the vector V equals 0 times the first basis vector plus 0 times the second basis vector and so on up to 0 times the nth basis vector. But if you just have 0 times something plus 0 times something and so on all the way to the end of the sum, then that entire sum just equals the 0 vector. All right, so yeah, if the coordinate vector equals 0, then the vector itself must equal 0. So that linear transformation is invertible, and therefore it's an isomorphism, and therefore the spaces that it acts on really are isomorphic to each other. So we're done. That's the end of the theorem. Okay? Great. And just as one sort of final corollary of this is that, well, it's not too hard to show that if you have vector spaces V and W that are isomorphic to each other, and then vector spaces W and X that are isomorphic to each other, then actually V and X must be isomorphic to each other. In other words, isomorphisms are transitive, okay? If this thing's the same as this, and this thing's the same as this, well, then all three of them are the same as each other, okay? So, one thing that you can do with this fact is, well, when you combine it with this previous theorem, what it tells you is that if you have any two vector spaces, doesn't matter what they are, if they have the same dimension, and they're over the same field, then they're isomorphic to each other. Okay, so that's our final fact. And actually this is if and only if, okay? If you have two finite dimensional vector spaces over the same field, so using the same scalars, then they're isomorphic if and only if they have the same dimension. So for example, R2 and R3, they're not isomorphic because they're 2 and 3 dimensional respectively. But R2, well, that's isomorphic to every single plane in R3 as long as they go through the origin, so they're really vector spaces. It's also isomorphic to the degree less than or equal to 1 polynomials, the 1 by 2 matrices, and so on. R4 is isomorphic to the 2 by 2 matrices. R8 is isomorphic to the degree less than or equal to 7 polynomials, and so on. You know these things automatically now because you only have to check dimensions. As long as the dimension is the same, they're isomorphic. If the dimension's not the same, they're not isomorphic. And that's all there is to it, okay? And it's because of coordinate vectors. Because if they have the same dimension, we can represent them by the same types of coordinate vectors. Okay, so in a sense, the idea here is that, you know, vector spaces being isomorphic, like, even though they look different on the surface, the labels for their vectors look different. Like maybe they look like a polynomial, maybe they look like a matrix, maybe they look like a list of numbers. But really, the way you do calculations in those spaces is no different. It's no more different than if you wrote down those vectors using different fonts. Okay, the choice of font doesn't matter. It doesn't affect the calculation, just like none of those other fine details affect the calculations. They don't affect the linear algebra at all. So they're isomorphic to each other. All right, so that'll do it for today's class. I will see you all for lecture 15 when we start talking about other properties of linear transformations. We already talked about invertibility. We're going to go on to other properties now, like range, rank, eigenvalues, and stuff like that. So I'll see you then.